Hey guys, it's Hazel and welcome back to ACE Tutoring. Welcome back to another ACE Explains video. Today I'm going to be teaching you guys how to draw Lewis structures. This is like a big thing that can trip up a lot of kids when they're doing chemistry, no matter what level of chemistry you're in. I'm currently taking college chemistry and I understand, okay? Lewis structures are not the easiest thing, so I'm here to break it down for you, hopefully make it a little bit easier, and that is what we are going to tackle today. So basically, the big thing to know about Lewis structures is that they are a visual representation of covalent bonding. So that is the only type of bonding that you see when you're talking about Lewis structures. So it's not ionic bonding. Ionic bonding is the transfer of electrons, right? Covalent bonding is the sharing of electrons. All of this is discussed in my basic bonding video and my ionic and covalent bonding videos, all linked down below. So make sure you check those out if you don't remember what I'm talking about. But covalent bonding is about the sharing of electrons. So when we're drawing Lewis structures, that is what Lewis structures are meant to represent. And I think that they were named after this chemist with the name Lewis, but it's not important. I don't remember who he was. The other thing to remember about Lewis structures is that they only represent the valence electrons of an atom or an element. So when you're looking at the periodic table, they only represent valence electrons. That's really, really important to remember because sometimes students get a little bit confused. They see an atom that's got like a number, like an atomic number of 24, and they're like, oh yeah, I need to draw 24 dots on my Lewis structure. Far, 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 far from true. So make sure that you remember that when you're talking about Lewis structures, that it is only the valence electrons, right? So for most atoms, that means you have a total of 8 dots on your Lewis structure, right? We'll be talking about exceptions later, but this is called the octet rule. And the octet rule basically states that the maximum amount of valence electrons that a Lewis structure, that an element can have is 8. So any given atom is looking to fill up their shell to get to 8 electrons, like we talked about in bonding. So the octet rule states that you should have a total of 8 electron pairs in your Lewis structure. Speaking of pairs, let's talk about bonding and non-bonded pairs. So we're going to start by giving ourselves a very simple challenge. We're going to do the Lewis structure of the element sulfur. So if you look on the periodic table, which I probably should have one up here, but I'll pull one up in a minute. If you look on the periodic table, sulfur has the atomic number of 16, and it is in group 6A on the periodic table, right? So on the periodic table, there's the main group elements, and then there's the transition metals in the middle, metalloids, and then more main group elements. If you look at the top of the periodic table, there are numbers going all along the top. You can tell the amount, you can tell the amount of electrons that an atom has by looking at the group number. So sulfur is in group 6A, right? So that means that it currently has 6 electrons. So I'm going to draw the Lewis structure for sulfur. We're going to start by putting a dot on all 4 sides. Similar to electron configuration and the Hund's rule, basically, this is kind of the same thing. You don't fill 2 at a time, you fill 1 at a time, and then you go back, right? So 6 electrons, so I'm gonna go 1 and then 2. Just like that, so that is equal. So these are 6 electrons. Remember, the octet rule states we want to have a total of 8 in our Lewis structure, so that means that it's missing 2 electrons. That's how you can use the periodic table to tell how many electrons an atom still needs when it shares, right? You can tell that by looking at the group number that's listed at the top of the periodic table where the atom is found. So, where the element is found. So sulfur needs 2 more electrons in order to be complete, right? So I'm gonna think of what has 2 electrons that can be given to sulfur. Oh, I have the best idea. So yeah, sulfur needs 2 more electrons to be complete. And let's look at another element on the periodic table. It is found in group 7. So it has 7 valence electrons, valence meaning the outer shell, 7 valence electrons, and it only needs how many to fulfill the octet rule? 8, exactly, because 7 plus 1 is 8. So it's missing that 1, right? So let me draw the Lewis structure for chlorine really quick. 1, 2, 3, 4, 5, 6, 7. Let's go with that. Right. So here is a good place to initiate a bond. This bond allows sulfur to share an additional electron with chloron, and it allows chlorine to share an additional electron with sulfur. So chlorine now has a full shell of 8 electrons, right? Because it's got 1, 2, 3, 4, 5, 6, 7, 8, right? Because it's sharing that electron from sulfur. Now, sulfur, on the other hand, is a little sad because it's still missing a partner for this lone electron that goes right there. So we don't have enough space in this drawing. In fact, actually, let me try to make more space by sizing this down a little bit because I want to make my example super clear. Okay. We will put another chlorine atom right here, and we will do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, right? So now, this other chlorine atom, same thing. It's got exactly how many electrons it needs to be a stable atom. 1, 2, 3, 4, 5, 6, 7, and 8. And now sulfur, who we're trying to fix, is also doing great. 1, 2, 3, 4, 5, 6, 7, and 8. So now all of the atoms are all stable, and so this is how you know that your Lewis structure is complete, right? So I want to bring your attention to what we are seeing here in terms of some vocab. So here we see 2 electrons that are together, but they are not being bonded with any of the other elements in the Lewis structure. These are called non-bonded pairs or lone pairs. That was honestly the entire point of this example, was just to tell you what a non-bonded or a lone pair is, as opposed to a bonded pair, which is seen right here in a pair of electrons that shares a bond across 2 elements. All right, hopefully we got the gist of it, because it's time to do some practice. So we'll just come right over here and we'll get started with this problem right here. So we have CH4, which is 1 carbon molecule and 4 hydrogen molecules. This atom is actually also known as methane gas. Now, when you want to start by drawing your Lewis structure, it is important to note that you want to center the atom that is closest to the center of the periodic table. So in that case, this would be carbon. It also helps that carbon, there's only 1 carbon and there's 4 hydrogen. So it kind of makes sense to the mind that you would put the carbon in the center and then have the hydrogen like around it. But if you can't figure out what goes in the center and what is surrounding, always use the element that is closest to the center of the periodic table, so going toward the transition metals. So we're going to put carbon in the center, and we're going to surround it by hydrogens. Now, when drawing a Lewis structure from scratch, a lot of teachers and a lot of places will teach you to do it differently, but this is the way that I have found to be most helpful. Instead of worrying about how many electrons you need to do pairs for, simply focus on each individual element and the amount of valence electrons that you know they have. And you can always use the periodic table for this. Now, like I said, I don't have it pulled up, but you should. So, hydrogen has one valence electron. So we're gonna put a valence electron next to hydrogen. Like so, like so, like so, and like so, right? Carbon has 4 valence electrons, given that it is in group 4 on the periodic table. Actually, yes, it is. It is in group 4. Okay. So we have 1, 2, 3, 4. Okay? So, when we're making bonds, we just look for 2 atoms that are alone and can come together, not atoms that are in a non-bonded or a lone pair. We don't want pairs. We want single atoms that can come together to make a bonded pair. So look what we have here. 1 bond, 2 bonds, 3, and then 4. And there we have the bond for methane. Quick and easy, just like that. How about H2O, right? H2O, we're gonna pick the molecule that is closest to the center of the periodic table. Although in this case, hydrogen is on one side, oxygen is on the other side, so it's like, So we're gonna put oxygen in the middle since there's 1 of oxygen. So oxygen goes in the middle, and H is gonna go on either side, right? We're gonna start by ascertaining or deciding how many electrons, how many valence electrons each element has based on where it is in the periodic table. So we know that hydrogen has 1 valence electron each, and oxygen has 6 because it is in group 6 on the periodic table. 1, 2, 3, 4, 5, 6. And there are the bonds. 1 and 2, right there. So we have some bonded pairs and some non-bonded pairs here for H2O, but everybody's got a full electron shell. Hydrogen has 2, oxygen has 8, and hydrogen has 2. So that is literally the art of Lewis structures, but we're going to tantalize our taste buds with some more difficult problems. I want to draw your attention to this problem right here, N2, I think that's the way to say it. N2 is an example of, and I think I talked about this in my covalent bonding video, a diatomic molecule. And a diatomic molecule is a molecule that can bond with itself. And remember, there are only 7 diatomic molecules, and I covered this in my other video. But since nitrogen is a diatomic molecule, it is going to bond with itself. So we are going to have 2 nitrogens in our Lewis structure. Nitrogen and nitrogen, right? We first start by figuring out how many valence electrons nitrogen has. Now, nitrogen is in group 5 on the periodic table, so we know what that means. 1, 2, 3, 4, 5. That sounds like a good idea. 1, 2, 3, 4, 5, right? So both of the nitrogens have 1 pair that's like a non-bonded pair, but we're not gonna leave that one alone, right? We're just looking at the single electrons that we see here, which are these 3. Now, something that is important to know when you're drawing Lewis structures is bonds do not just have to be atom-to-atom bonds. There can be double bonds, and there can even be triple bonds. Nitrogen, for example, has a triple bond because in order to fix the issue of having 3 unbonded electrons, we need to bond them all to one another quickly and simultaneously. So the bonds are drawn like this. And that fixes the issue because this creates 6 plus 2 plus 2, and each nitrogen atom will have 8 valence electrons in total. Pretty neat, huh? So this is an example of a triple bond. I'm sure we're gonna see some double bonds in some of the other problems, so don't worry if you're still confused about what I said. But a triple bond is just 3 sets of atoms in a column that bond to another 3 sets of atoms also in a column. The limit is triple bonding. You cannot go past 3. So that's always nice to know. So you have single bonds, double bonds, and triple bonds. Let's try some challenge problems. So we have C2H6, meaning that we have 2 carbons, 6 hydrogens. We're gonna start with carbon. Carbon's a little bit closer to the middle. Let's see how we are going to go about this. We've got 6 hydrogens, but we only have 2 carbons. I'm gonna start by bonding those carbons to one another. So 1, 2, 3, 4, 1, 2, 3, 4. Then I'm gonna move the hydrogens to surround it. What I'm thinking is 1, 2, 3, and 1, 2, 3. And each hydrogen, like we know from some of the other examples, has 1 valence electron each. Here's the fun thing. Carbon is going to make this bond right here, and hydrogen and carbon are also going to make all of these bonds right here, but we don't want to go too quick. We don't want to get too ahead of ourselves. We need to count and make sure that every single element has reached a full octet of 8. I just think that I maybe forgot to mention hydrogen can only have 2. You've probably been wondering that this entire time. Hydrogen is an exception to the octet rule, and it only seeks 2 valence electrons. You may remember this from your chemistry class, but I thought I would make a note of it since we've been doing lots of examples with hydrogen and I never told you. Okay, so 2, 4, 6, 8. Bingo! That's for carbon 1. And then we have here 2, 4, 6, 8 for carbon 2. And every single hydrogen has 2 electrons as well. So here we have a completely well-drawn Lewis structure. Over here, we've got CH2O. Now be careful with this one. People are very quick to think that it's carbon being bonded to H2O, but that is not the case. We're gonna put carbon in the middle, and we're gonna remind ourselves that carbon has 4 valence electrons. 1, 2, 3, 4. I'm going to put 2 hydrogens on the outside of carbon that can bond with the electrons that are here, right? So I've already got 2 bonds in the works. I just have 2 more. Oxygen, if you remember, has how many? 6. 1, 2, 3, 4, 5, 6 valence electrons. Now, as a chemistry enthusiast, I see what's happening here. We have 2 single electrons on either element, on either atom. The natural thing is to put them together in a double bond. So we're witnessing a double bond for the first time in this video. Oh, the whole thing is traveling. Okay. Yeah, it's doing it again. Here we go. And so we're gonna put them and group them together like that, right? So let's do a little check. Carbon has 2, 4, 6, 8. Hydrogens have 2 each. Oxygen has 2, 4, 6, 8. And when I say 6 and 8, I'm counting the lines because the lines signal 2 electrons. So each element in this Lewis structure has a completely full valence shell. So exciting. Okay, let's do a few more. Let's do one big challenge problem. So here we have CH3NHCH3. Oh my gosh. What I'm seeing here is that we should divide this up into 3 sections. Section 1, Section 2, and Section 3. So I'm going to separately do the CH3 Lewis structures and then combine them with the NH. And in my head it's working, so hopefully it also works on paper. C, H, H, H. We know that carbon has 4 valence electrons and that hydrogens only carry 1. Right now we have a bond, and a bond. So we're missing 1 bond that goes there. And there's another CH3. Oh, I wanted to duplicate it. Just like that on the other side. This is like movie magic. I'm like just moving stuff all over the place. But you get the picture. And then there's that last electron that goes there, right? So just draw this on your own paper since you can't maneuver like I can. Then we have NH. Nitrogen, we might recall, has 5 valence electrons. 1, 2, 3, 4, 5. And hydrogen, we also might recall, has 1 valence electron as well. Now I'm not gonna go so far as to bond yet. I want to assess what I have. I've got it. This is what we're going to do. This hydrogen is actually going to bond under the nitrogen, and that's perfectly okay. We're going to move the free single electrons on either carbon closer to the nitrogen, like so. See that? So using the 3 free electrons, I was able to create 3 additional bonds. We leave these 2 alone since they're already in a pair, and now we count just to make sure. We gotta count just to make sure. Hydrogen's got 2, 2, 2, right? So we have 2, 2, 2 for hydrogen. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. And then on the other side, hydrogen's got 2, 2, 2. And then carbon has 1, 2, 3, 4, 5, 6, 7, 8. As far as nitrogen goes, nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Okay, I know that's like a lot of confusing dots and counting and stuff, but if you do some practice, I don't know how to say this, as you practice, you will slowly come to understand how it works. So don't feel discouraged that you're not picking it up right away. Practice literally does make perfect. So I hope that this has made sense for you guys. If you have questions about any of the Lewis structures on your homework, please drop them in the comments below and someone from our team will answer them. As always, tune into our other chemistry videos that we have posted in the playlist on our page, and subscribe so that you can be updated when a new chemistry video is posted. All right, see you guys. Bye-bye.